A contemporary to the global routing algorithm is the distributed routing algorithm, in which the global picture does not exist with individual nodes. Rather, each node maintains its local information, and this local information is accumulated across all the nodes and eventually forms the big picture. Distance vector is a well-known example of the distributed algorithms. In this module, we shall understand the details of distributed algorithms, distance vector as its base class, and we'll also determine its complexity. The reference that I've chosen is again from Kuros and Ross. Distance vector as the base or an example distributed routing protocol is best understood when you imagine that a router just knows its physically connected immediate neighbors and their associate costs. So when a routing process starts, two routers on a network would discover each other through the incremental and stepwise notifications coming from their neighbors and spreading over the whole network. So it's an iterative process. The exchange of information only restricted to neighbors is, of course, giving us a hint that compared to the link state, distance vector would involve less broadcast overheads. The key idea in distance vector is that each node maintains and sends its own vector of distance to all of its neighbors, That is, first it determines what are its neighbors, what are the distances to its neighbors. It manages a vector because a vector has two values, distance and direction. So that is why the name. So when a node, say X, receives new distance vector estimate from its neighbor, this heralds or announces a change in the topology. So it updates its own distance vector correspondingly using the classical Bellman-Ford equation. The Bellman-Ford equation is a dynamic programming model. It gives us a perspective of building the information in a graph by starting from one side and slowly moving to the other side. Let's assume that we are interested in determining the least cost path between a source X to a destination Y, represented as d sub X of Y. It can be actually broken down into two costs according to the Bellman-Ford equation. That is, the cost of going from X to Y would involve the minimum cost path such that the cost from moving from X, which is the originator, to one of its neighbors is the minimum, and then from that neighbor to the destination is also minimum. Since we are sitting at X and we are doing the route discovery sitting at X, and we only have access and reachability to our one hop neighbors, that is V, so we leave it up to V to do the same process as we are doing sitting at the originator. So this process keeps on repeating itself in an iterative way, and eventually the destination is discovered. Distance vector is far less complex as compared to link state because the information is being shared amongst the neighbors only. The overall speed and convergence time is highly dependent upon, number one, the topology size, because it's linearly related to the topology size, and number two, if there are some potential loops. So if there are loops, there would be more than one distance vector updates. So it is going to take some time before these distance vector updates converge onto the true picture of the root and cost change.